Welcome to another deep dive. We're tackling some pretty fundamental geometry today. Spheres and cones.
Yeah, some classic shapes.
And the material you sent over was really interesting. It's kind of like um, almost a playful approach to understanding these shapes.
Definitely. It's from a textbook chapter on surface areas and volumes, and it emphasizes this hands-on approach with activities and real-world examples.
Yeah, and you mentioned wanting to go beyond just formulas, right? Like actually getting that moment of understanding with these three-dimensional shapes.
Exactly. It's not just about plugging numbers into equations, but really grasping the why and the how behind those calculations for cones and spheres.
So for this deep dive, I guess our mission is to extract the most important insights from this source material.
Right. Yeah, present them in a way that's clear, engaging, and hopefully leads to some of those ha-ha moments you're looking for.
All right, let's dive in. First up, cones. Now, the source we're looking at today is very specific about what makes a right circular cone. What exactly does that mean?
Oh, yes, the right circular cone. It even shows us some shapes that don't fit the description.
Right, like to illustrate the point.
Exactly. So to break it down, the right part means that the line from the tip of the cone, the vertex, goes straight down to the center of the base at a perfect 90-degree angle. It's like a perfectly upright ice cream cone.
Got it. So no leaning towers of tones allowed.
Aha, exactly. And then the circular part, well, that means the base of the cone has to be a perfect circle. No squares, triangles, or any other shapes for our base.
Okay, so we've got our classic cone shape in mind. Now, how do you even create that shape geometrically? The source mentioned a neat mental exercise.
Yeah, they describe this really cool way to visualize it. Imagine a right-angled triangle, the kind with a 90-degree corner.
Yeah, we remember those from school.
Now picture taking one of the sides that makes up that right angle and spinning the whole triangle around it.
Oh, I see. So like using that side as an axis.
Exactly. And as you spin the triangle, the other two sides trace out a path, and that path creates the cone. The side you spun around becomes the height of the cone. The other side becomes the radius of the circular base, and the hypotenuse of the triangle, well, that becomes the slant height of the cone.
Wow, that's a really clear way to picture it. It's like a triangle transforming into a cone through spinning.
Yeah, it's a pretty elegant way to see how a 2D shape can create a 3D one.
And you mentioned slant height. There's the slant height, the height, and the radius. They're all connected somehow, right? Something about the Pythagorean theorem.
You got it. It all comes back to that trusty theorem. If you look at the triangle we used to create the cone, you'll notice that the slant height is the hypotenuse. And the Pythagorean theorem tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides, which are the height and the radius. So we have L equals R plus H arrows.
Okay, so that's a key relationship to keep in mind. Now let's move on to surface area, specifically the curved surface of the cone. The source material has another hands-on activity for this one cutting and unfolding a paper cone. What's the point of that?
This activity is super insightful because it helps us understand how to calculate the curved surface area. Imagine taking a paper cone and making a straight cut from the vertex all the way down at the edge of the base along the slant height.
So like slicing it open.
Exactly. Then you carefully lay it flat. What you end up with is a sector of a circle. It's like a slice of pie, basically.
Interesting. So a cone turns into a pie slice.
Yep. And the radius of that pie slice is actually the slant height of the original cone and the curved edge of the sector. Well, if you line it up, it matches perfectly with the circumference of the cone's base.
Oh, that makes sense. So it's like we're unraveling the curved surface into a flat shape.
Precisely. And once it's flat, we can use what we know about circles to figure out the area.
So how do we actually get to the formula for the curved surface area from this pie slice?
The book has a clever way of explaining this. They suggest you imagine dividing that circular sector into thousands of tiny little triangles.
Like really, really small slices of pie.
Exactly. And all those tiny triangles have their points meeting at the center of the circle where the vertex of the cone used to be. Now, the height of each of those tiny triangles is basically the slant height of the cone. And all their bases, when you add them all up together, make up the curved edge of our sector, which we know is the same as the circumference of the cone's base.
Right.
I'm starting to see where this is going.
Now remember, the area of a triangle is half base times height. So if we add up the areas of all those tiny triangles, we get something really close to half times the slant height times the total length of all the bases.
Which is the circumference.
You got it. So that's 12, 2p, and that simplifies to just trip p. That's the formula for the curved surface area of a cone.
Wow, so we basically used a bunch of tiny triangles to figure that out. It's amazing how that works. Yeah, it's a really neat way to see how we can approximate a curved surface with simpler shapes and still get an accurate formula.
Okay, so parallel for the curved surface. What about the total surface area of the cone? We need to include the base too, right?
Of course, to get the total surface area, we just add the area of the circular base to the curved surface area.
And we know the area of a circle is parallel.
Exactly. So the total surface area of the cone becomes Pearl plus Arwell. And we can even simplify that a bit by factoring out par to get par L plus R.
Okay, that makes sense. Curved surface plus the base equals total surface area. Now, the book includes a couple of straightforward examples to practice these formulas.
Yeah, those examples are there to help you get comfortable using the formulas. In one example, you're given the slat height and radius, and you just plug them in. In the other, you need to use the Pythagorean theorem to find the slat height first.
It's like a little warm-up before we get to the real-world problems.
Right. And speaking of real-world problems, there's this really cool example about corn cob.
Oh yeah, the corn cob. That one was fun. They actually used the surface area of a cone to estimate the number of kernels on a corn cob.
I know, right? It's a pretty unique application. They simplify the shape of the corn cob to a cone, then they calculate the slant height and the curved surface area, and finally they use a given number of kernels per square centimeter to get their estimate.
Yeah, it's like they're turning a corn cob into a geometry problem.
Exactly, and it shows how these concepts can be applied to everyday objects. Even if it's just an approximation, it gives us a way to think about surface area in a more tangible way.
It definitely makes you look at corn on the cob a little differently.
Haha, for sure. Now that we've tackled surface area, let's move on to volume. And the book has yet another hands-on experiment, this time with sand, a cone, and a cylinder.
Oh yeah, this one was interesting. They basically show that a cone holds 1/3 the volume of a cylinder with the same base and height.
Yeah, it's a very visual and convincing experiment. Imagine you have a cone and a cylinder with the same base radius and height. You fill the cone completely with sand and then pour it into the cylinder.
And it only fills up 1/3 of the cylinder.
Exactly. You'd need 3 cones full of sand to completely fill the cylinder.
That's such a simple but effective way to demonstrate the relationship between their volumes.
Right, and it leads us directly to the formula for the volume of a cone. It's basically 1/3 the volume of a cylinder with the same dimensions.
So that 13 factor makes perfect sense now after seeing that experiment.
It really helps solidify the concept. The book then goes on to provide more examples like calculating the volume when you only know the slant height and height, which means you need to use the Pythagorean theorem again to find the radius.
Right, got to put that theorem to work.
And there's another example about a canvas tent that requires both surface area and volume calculations.
Oh yeah, that one was cool. It showed how those concepts can be intertwined.
Exactly. In the tent problem, you have a limited amount of canvas, which relates to surface area, and you use that to figure out the dimensions of the tent and then calculate how much space is inside, which is the volume.
It's a great example of how these concepts can be used together in a real-world design problem.
It really highlights the practical applications of geometry.
Okay, we've conquered the cone. Let's move on to something even rounder, spheres and hemispheres. Now, it's easy to get circles and spheres mixed up. They're both round. But what's the key difference between them?
That's a great question, and it's important to distinguish between the two. As the book points out, a circle is a flat, two-dimensional shape. It exists only on a plane, like a drawing on paper.
Right, like a coin.
Exactly. A sphere, on the other hand, is a three-dimensional object. It's like a ball. It's defined as all the points in space that are the same distance away from a central point.
Okay, so a circle is flat and a sphere is a solid object.
Precisely. And the book shows that you can actually create a sphere by rotating a circle around its diameter, just like how we spun a triangle to make a cone.
Oh, that makes sense. So it's like taking a circle into the third dimension.
Yep. Now, figuring out the surface area of a sphere seems a lot trickier than a cone, but the book describes a really clever experiment using string.
String, how's that work?
It's surprisingly simple but effective. Imagine taking a long piece of string and wrapping it tightly around a sphere like a ball of yarn.
Okay, I can picture that.
Once you've covered the entire sphere, you carefully unwind the string. The experiment then asks you to see how many flat circles with the same radius as the sphere you can completely fill with that same length of string.
That sounds interesting. I wouldn't have guessed how this turns out.
The surprising result is that you can fill exactly 4 circles.
4 circles. That's unexpected.
It is, and that leads us to the formula for the surface area of a sphere. For Paris, it's essentially 4 times the area of a circle with the same radius.
Wow, that string experiment really makes that formula stick. It's such a visual way to understand it.
It really connects the 3D surface of the sphere to the 2D area of a circle.
Okay, now let's talk about hemispheres. What happens when we cut a sphere exactly in half?
When you slice a sphere right through its center, you create 2 identical halves. Each of those halves is called a hemisphere.
It's like cutting an orange in half.
Exactly. Now, when we think about the surface area of a hemisphere, it's not just half the surface area of the sphere, right? Because now we have that new flat circular surface where we made the cut. You're absolutely right. We have to consider both the curved surface and that new flat base. The curved surface area of a hemisphere is indeed half the surface area of the whole sphere, which is 12, 4 pro equals 2 pro.
Okay, so 2 par for the curved part. What about the total surface area?
For the total surface area, we add the area of that circular base, which is par for a. So the total surface area of a hemisphere becomes 2 par plus par equals 3 par.
Got it. So the total surface area is 3 par, and the curved surface area is 2 par. It's important to keep those separate.
Absolutely. And as always, the book gives us some examples to illustrate these concepts. There's one about calculating the surface area of a hollow sphere, like the kind used for motorcycle stunts.
And there was that one about painting a hemispherical dome, right?
Yeah, that one's a good example because you're given the circumference of the dome and you have to work backward to figure out the radius before you can calculate the surface area.
It shows how these formulas can be applied in different ways depending on what information you're given.
Exactly. Now that we've covered surface area, let's dive into the volume of spheres and hemispheres. And it looks like we're back to water displacement.
I'm sensing a pattern here with these hands-on experiments.
They're definitely effective. So for this experiment, you submerge a sphere completely in a container that's full of water. The sphere pushes some of the water out of the container, right?
Yeah, the water level rises.
And the volume of water that spills out is exactly equal to the volume of the sphere. By carefully measuring that displaced water and relating it to the sphere's radius, we get the formula for the volume of a sphere.
So for the sphere, and since a hemisphere is half a sphere, what's its volume?
It's pretty straightforward. It's just half the volume of the sphere. So the volume of a hemisphere is 12, which simplifies to over.
Makes sense. And the book provides some practical examples for these formulas, too.
Oh, definitely. There's one about calculating the mass of a shot put, given its radius and density, and another one about figuring out how much liquid a hemispherical bowl can hold.
Those are great examples of how these seemingly abstract formulas can be applied to real-world situations.
They really ground the concepts in something tangible.
Okay, so let's recap. We've explored right circular cones with their Kirk surface area, Pearl total surface area plus R in volume. Then we moved on to spheres with their surface area, two Kainohoras, total surface area and volume. And those hands-on activities really helped us understand the why behind the formulas.
Absolutely. Those visual aids and analogies are so powerful in making these concepts stick. It's so much more engaging than just memorizing equations.
So as we wrap up this deep dive, I challenge you to look at the world around you with these geometric lenses in mind.
Yeah, see if you can spot cone spheres and hemispheres in everyday objects.
Think about how you might estimate the surface area of a basketball or the volume of an ice cream cone.
It's a fun way to apply what we've learned.
And maybe you can even start to appreciate the geometry involved in architecture and design.
It's all around us.
Thanks for joining us on this deep dive into cones and spheres.
It was a pleasure exploring these shapes with you.
Until next time, keep those brains buzzing.